I work at the University of Padova in Italy. My work consists of a part of investigation and a big part of mentoring students, both master and PhDs. My main interests are, let's say, cosmology in the broadest sense, how we can probe the universe both in its very first instance and also today. And then the core of my research is how gravitational waves can help us studying the structure of the universe. Gravitational waves are one of the most astonishing predictions of the theory of general relativity developed by Albert Einstein more than a century ago. In its theory, he joined together the concept of space and time into a single entity that now changes depending on the content of space-time itself. So when we have two very massive objects like black holes that are also very dense, we observe like a deformation of space-time. And when these two objects, for instance, merge together, they create a wave that propagates across the universe and ultimately reaches us. These waves are so tiny that deforms the space-time near us by fraction of an atom. So we cannot perceive it in our daily life. Gravitational waves are interesting because they allow us to study the universe in a complementary fashion with respect to what we are doing now with electromagnetic waves, which means light in different wavelengths. And they allow us to study the same phenomena, but with a completely new tool. Like their discovery or their detection, if you want, is on the same level of scientific novelty as the invention of the telescope in the 16th century. Searching for gravitational waves require a huge technological advancement, and it took like 100 years to detect the first one. The most important instrument we are using today to detect gravitational waves are interferometers. This kind of instrument uses laser light to detect changes in the relative position of objects. So we search by them by measuring distances between mirrors to a very high precision, since we are trying to measure like changes in distance by like the order of fraction of an atom. Gravitational waves is gonna change the relative position of mirrors, and by measuring like this tiny variation we are able to understand the properties of the gravitational waves and in turn to understand the properties of, for instance, black holes that generated the wave. SKAO will detect the effect that gravitational waves have on the signal we receive from pulsars that live in our galaxies. These pulsars are an extremely precise clock, in the sense that we can predict very accurately when we're going to receive their signal. The main goal of the SKAO gravitational wave working group is going to be the characterization of these gravitational wave signals. In particular, we want to explore what generated this signal and whether it's, for instance, a supermassive black hole binaries or some more exotic model. I started getting interested in SKA during my PhD, where I remember I also attended the conference here in Granada to celebrate the entrance of Spain in the SKA organization. Later, my involvement increased, and now I'm like a gravitational wave working group co-chair. I'm very excited about working on gravitational waves. This new field really opened up a new way of studying the universe and allowed us to understand a set of phenomena that previously was totally unknown. Also, as a young researcher, you always wonder how I'm gonna carve some space for me in a field that has been in place for so many years. And this, the opening of a new field really gives an opportunity to a lot of young people to do science at the forefront.